Okay, so now we're up to figuring out how we can name ionic compounds. You will have had some practice with this before, but it's keeping in mind this time that now we don't have a table of valencies and we need to be able to both name and draw the formulas for our ionic compounds. So, as with most things, there are rules for how we go about actually naming our ionic compounds. Okay, generally they have two word names, and the first word in the name is always the cation, so our positive ion, and the second word of the name is always the anion. So if we look at this example here, we have sodium chloride, where we have the cation, which is coming from our sodium atom, and our anion, which is chlorine with an extra electron, so forming chloride. And when we bring those two together, we get sodium chloride as our name. So we have the cation first, we have our cation first, and then we have our anion. Okay, and then if we look at our magnesium hydroxide example, even though this is a polyatomic, so we've got more than one atom forming our anion, we have our magnesium cation first. Okay, so our cation, and then we have the hydroxide, which is our anion. Anion second. Okay, so the best way to approach this in terms of naming an ionic compound is to always look at the formula, then identify the cation, your anion, and then put their names together to get the name of the compound. So if we look at something like this, okay, this will be our cation, and if we look up this symbol on the periodic table, we should identify that this will be aluminium. And then we have a polyatomic again. This one is actually nitrate. Okay, hopefully you'll remember this one. It is an NO3 minus. Okay, so we don't need to deal with this number here. We don't put di, tri, or anything like that. We just use the name. So now this would become aluminium nitrate. Okay, so the trickiest thing to this is remembering the names of our anions. Okay, so just here, so now we've got a couple more examples. Here we have our compound formula. In this time we've got CaCl2. Okay, and then the cation, so we're going to name the first one here Ca, well that's calcium, and it stays the same as its element name. And then Cl, well that's going to be our chloride anion, so we're going to have calcium chloride. Okay, now where we see a little bit of variation is where we have transition metals. So in this case, our cation is going to be copper, but copper can have different charge states, so either +1 or +2 or different things like that. So now when we have our name, we need to make sure that we have copper, the name of our cation, and then we use a Roman numeral, in this case 1, to dictate what the charge is on it. And we know that this one is going to be copper 1 because I have 2 coppers and just 1 oxygen. And hopefully you remember that oxygen forms 2 minus anions. So this means that we'd need 2 of the coppers to form our oxide, copper oxide. So we have copper 1 oxide. So we get the full compound with the Roman numeral there. Okay, and then we can do that the other way, going back from our name to a formula. So if we were told copper 1 oxide, then we look at it and we can see we have copper and oxide. So we would have copper 1 plus as our cation and oxide, oxygen 2 minus as our anion. So all our main block elements, so our S and P block, okay, so S and P block, okay, which are on our periodic table. They're going to be our main block elements, so our not our lanthanides and not our transition metals. So our S and P block elements, okay, they for the cations of those, we always just use the name of the element. Okay, so if it's a positive ion, we use the name of the element. So things are a little bit different when we look at cations for the transition metals, as we saw just before, where we need to give our Roman numeral. So in our D block, because they have variable charge states or variable oxidation states, okay, we need to specify what one we're talking about when we name them. Okay, so iron can be a +2 or a +3. So if we have iron here, iron 3+, we give it iron 3. The old way we used to name these was we used to use the terms ferric or ferrous. And it's always much trickier to remember which one was +2 and which one was +3. Now, with naming conventions, we just specify what the charge is by specifying the Roman numeral. Anions, well, anions are a little bit different. When the only atom in it, we use its name, but we change the ending. Okay, so for sulfur, say we have sulfur, okay, it will form the anion sulfide, okay, which tells me that it only contains sulfur, so it would be S, and then if I look this up on the periodic table, I'd see that it's going to form in group 16, so it'll need 2 electrons and it'll form S2- ions, okay. Oxygen becomes oxide, sulfur becomes sulfide, nitrogen. Have a go and write down what you think nitrogen will be. Pause the video and then come back for the answer. Okay, so nitrogen, okay, nitrogen will form a 3- ion and that we actually call nitride. Okay, it's our nitride ion. So any compound ending in IDE tells us there's only one element, okay, in that part of the compound and that it's an anion. Okay, so in this case, sodium nitride, we've got the IDE, so it'll be NaN. Okay, so just going through our names, first element in the compound is our cation. If it has a anion name that ends in IDE, then it's another elemental anion. Polyatomic ions are ones that you need to know, and there's a number that you need to know for the IB, okay? But essentially polyatomic ions, poly means many, okay? So these are ions that contain more than one atom. So these are the ones that we put into brackets. So ammonium, oops, that's ammonia. So let's change that. Ammonium, okay, is one, or we may have cyanide, which is CN, the cyano group, and then carbonate. And you can see here the ammonium ion, when we draw these, we're saying this is the structure, and then the overall molecule has a charge of +1. Okay, or in the case of the nitrate anions, the overall molecule has a charge of -1. So they can be positive or negative. This one here, ammonium, is pretty much one of the only positive ones we deal with in our course. Okay, so let's see what these look like. We've already looked at the fact that the ending can give us a lot of information. So if it ends in IDE, then it's one element of the anion is the compound. If it ends in ATE, this tells us that essentially there's more than one element and the other one is oxygen. Okay, so if it ends in ATE, then there has to be an element combined with oxygen. So carbonate means that it's carbon combined with oxygen. Okay, and we see that in the carbonate anion, which is CO3 2-. Okay, and this is calcium carbonate. Hydrogen sulfate, we have hydrogen, and then we have the sulfate anion, which is SO4 2-. Okay. Then the tricky one, and these are the ones that you need to know, is that ITE means that it has less oxygen, one less oxygen than the other one. Okay, so basically we have this set of rules that the numbers of oxygen in our anions, so the root, which is like the name of the element, plus ATE means more. Okay, if it's per root 8, so per chlorate, that's the most. We don't see these often. Okay, not seen very often in our course. They'll usually give you the formula. You just sort of need to know that they exist. Okay, so usually I would say learn sulfate. So say this is sulfate, okay, and then sulfite is one less oxygen, but it has the same charge. I just got the charge wrong there. So it has the same charge, okay, so SO3 2 minus. And then hypo, so hyposulfite would be less than that, okay, so SO2, which we don't see. Okay, so there's some examples there: perchlorate, chlorate, chlorite, and hypochlorite. Okay, so these are all the ones of chlorine combined with oxygen. Okay, so 8 means a lot with oxygen, then ite means one less with oxygen, and they keep the same charge. This is all the polyatomic ions you need to know and be familiar with for this course. Okay, so you need to know nitrate, okay, so nitrate, hydroxide, sulfate, carbonate, phosphate, ammonium, and hydrogen carbonate. Okay, so I want you to see if you can write the names around each of these structures. So pause the video, write the names on each of the structures, and then come back to see if you got them right. Okay, so let's go through the names of these. Okay, so this one is going to be nitrate. Okay, it's our NO3 minus. This one is phosphate. We've got phosphorus in the middle with 4 oxygens. This is a really important one for biology. It forms the backbone of our DNA. Okay, we have phosphate groups on our DNA. This is hydroxide. This is the carbonate. Sulfate. What have we got here? This is the hydrogen carbonate. And of course our ammonium. Not to be confused with ammonia, very different, ammonium. Okay, so you need to learn all of these, so make sure these go into your notes. Okay, this is where things get a little bit funny, and we'll look at some of these in class as well. Okay, so there's a number of ionic compounds that can trap water in their ionic lattice. Okay, and that's what we see here. These water molecules are inside a complex lattice. Okay, so they're not bonded to, they're not forming part of the lattice, but they get stuck in the gaps. Okay, and when this happens, we call these hydrates. So basically things that are hydrated with water. Okay, when you heat a hydrate, so if you take a sample of a hydrate and you heat it up, of course you'll get water vapor coming off. Okay, so then it will change, you'll get a change in mass. Okay, and we can work out how much water is in there by heating it. Okay, so if we look at the example we have here, we have iron 2 sulfate octahydrate. Okay, so iron 2 sulfate, Fe, it's going to be 2, so it'll balance out the sulfate nicely. SO4 dot tells us it's a hydrate or complexed. Okay, not actually bonded in this compound here. And then octahydrate, well, octa is 8, and then we've got hydrate, so it's H2O. And so our formula will be FeSO4 dot 8 H2O, which tells us there's 8 molecules of water for every formula. We often see copper sulfate ones too, which are CuSO4, copper sulfate, dot 5 H2O is a common one that we'll use in the lab. Okay, so we know by the prefix, okay, octa or pentahydrate, how many water molecules will be present in the hydrated compound. Okay, so the prefixes are the same as the ones we tend to use in maths. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. So this would be 1 water, 2 waters, 3, 4 water molecules, 5 water molecules, 6 water molecules. So the one that we looked at before, which was CuSO4 dot 5 H2O, I want you to try and come up with the name for that. Pause the video and let's see what name you come up with. Okay, so welcome back. Hopefully you managed to figure out that this is going to be copper. Okay, it's a transition metal, so we need to specify the charge. Well, this is SO4, so this is sulfate, and it'll have a 2- charge, so this must be copper 2, and then sulfate, and then 5, that means penta, so it's going to be copper 2 sulfate, pentahydrate. Okay, and these are interesting because our hydrates and anhydrous salts actually often have different colours, like this one here with our cobalt salts. Okay, well that's it for this one. Hopefully you have gone through, you have your notes, and we can have some practice writing and naming our ionic compounds and writing some different formulas when we get into class.